This is the second video for the Achieve homework assignment in section 4.2. We're starting at number 17 in this video. It's a pretty easy rational function here. You can see we have f of x is equal to x squared plus 6 over x minus 4 on the interval 5 to 6. And we're supposed to find the maximum and minimum values on that interval by finding the critical points and evaluating any critical points between 5 and 6 along with the endpoints 5 and 6. Well, there really wasn't much to this problem for the main reason that similar to number 15 before, neither the critical points of this function were within our region. So notice I took my rational function that they gave me, x squared plus 6 over x minus 4. I tried to find the critical points by taking the derivative. I took that derivative with the quotient rule. I said the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which was just 1. Then I simplified and said, I know I'll have a 2x squared minus a 1x squared for 1x squared. Then I'll have negative 4 times 2x for minus 8x, and I'll also have a minus 6. Now, all of that's over my denominator squared, but I know the only way a fraction can equal 0 is if the numerator equals 0. So the critical points are going to be when that numerator equals 0. That doesn't factor, so I took the easy way out and just used the quadratic formula. But that quadratic formula didn't lead me to any critical points that would be between 5 and 6. So I went to my calculator, got the decimal approximations for 4 plus and minus the root of 22. That's pointless though, because neither of those are values in our region of interest. So now I said, well, okay, then my only possible maximum and minimum value could be at the endpoints. I evaluated my endpoints. When I plugged in a 5, I got 25 plus 6 is 31 over 5 minus 4. Obviously, 31 over 1 gave me a 31. When you plug in the 6, you know you'll get 36 plus 6 is 42. Divided by 2, 42 over 2 is 21. So we have a minimum at 21 and a maximum of 31. And I entered in that maximum minimum value, and that's all Achieve wanted for that problem. For the next one here, similar. I still have a rational function. This time the interval is 1 to 6. So I'm trying to find the maximum and minimum value of that function on that interval. So the process I did to solve that problem, I took my rational function on this interval and I said, well, I need to take its derivative. The denominator times the derivative of the numerator, which is just 1, minus the numerator times the derivative of the denominator, which came out to be 2x plus 8. Now, I tried to show my work here. I knew I'm subtracting this entire product, so I went ahead and FOILed out that product and remembered that I'm still subtracting everything inside the group. When I FOILed it out, I had 2x squared plus 8x minus 2x for a total of plus 6x, and then, of course, the minus 8. But now when I take this group minus this group, I'll get a negative x squared, and I would get a plus 2x, and a minus a negative 8 gives me plus 8. But now I said, okay, now I need to set that derivative, which is the entire quotient, equal to 0. The only way a fraction can equal 0 is if the numerator equals 0. As soon as I saw that, I knew that I would have this set equal to 0. I didn't want to set a quadratic equal to 0 with a negative x squared term. So the only thing I've done from here to here is I've just multiplied everything in this numerator by negative 1. You know you can do that because obviously you can multiply negative 1 on the other side and it's still 0. That's where I got the positive x squared minus 2x minus 8 equals 0. At that point, it factors really nicely. You can say factors of negative 8 that sum to get to negative 2, negative 4, and 2. This is going to yield, once you use the zero product property, that our critical points are at x equals 4 and x equals negative 2. Now, the critical point x equals negative 2 is not relevant to this problem because we're only concerned with the closed interval between 1 and 6. So I took the endpoints 1 and 6 along with the critical point in between them, plugged them into this equation. You'll see when I plugged in a 1, I had a 0. When I plugged in a 4, I had a 1/16. And when I plugged in a 6, I had a 5/84. Well, that 1/16 is just slightly greater than 5/84. And 0 is clearly our minimum. So I went to achieve and put 0 for my minimum value and 1/16 for the maximum. And that's what they were wanting. For number 19, a lot of these problems are extremely similar. Now, in 19, we've had one like this before. Anytime you have a square root, you always have to watch out for critical points where the derivative doesn't exist. It's not going to be an issue in this problem because what's inside the square root is guaranteed to be positive anyway. So x squared plus 1 is guaranteed to be positive. So I'm not going to have any critical points from which the derivative does not exist where the original function does. That's not going to be an issue. The original function has an infinite domain from negative to positive infinity. So I just go in and I start taking the derivative, setting it equal to 0. Here's my work for that. So I said, here's my original function. Notice again, I said instead of the square root of x squared plus 1, I said it's the group to the 1/2 power. That makes it more straightforward in taking its derivative. The 1/2 came down, multiplied the 8 to give me a 4, times the group to the negative 1/2, multiplied by the derivative of the inside, which is where I got the 2x. Now, minus the derivative of 5x, which is where I got my minus 5. Now I need to set this equal to 0. I went ahead and simplified this first. I said this first group is going to be 8x divided by the square root of x squared plus 1. And then I have minus 5. When that's equal to 0, I'll have the x values that yield my critical points. So I had to solve that. I moved the 5 to the right-hand side first step. Then I said, well, let's go ahead and multiply by that square root on both sides. So I had 8x is equal to 5 times the square root of x squared plus 1. At that point, I said, I knew I couldn't solve for x as long as it's inside of a square root. So I went ahead and squared both sides. 8x quantity squared is 64x to the second. And then if you square the entire right-hand side, 5 squared is 25. The square root squared is just the group x squared plus 1. Now I can say, okay, I know I would have 64x squared on the left and I would have a 25x squared on the right. If you subtract 25x squared on both sides, you're left with 39x squared on the left, and then you'll still have 25 on the right. Now we solve for x squared. X squared is going to equal 25 over 39. Then we take the square root, and you can say, well, x is going to be the square root of 25 over the square root of 39. That's 5 over the root of 39. Technically, it would be positive and negative. I didn't even bother putting the negative because I knew that my region was positive numbers only. So I can say, well, all right, my critical point here that's going to go into my problem is 5 over the root of 39. And now I just evaluated that original function at each of these x values, the 2 endpoints and my critical point. And you can see that the lowest value out of these 3 y values I got was the 6.245, and Achieve wanted this answer rounded to 3 decimal places. And the highest value occurred at the last point, and that was a y value of 10.298. And so now you can see that those are the 2 values I entered in on Achieve, and everything went fine. The next one, again, very similar. In fact, it's extremely similar problem. I had a radical expression minus 5x here. Now I have a radical expression minus 5x in this one. This time it doesn't have any term multiplying out in front of the radical. So I can say, well, just like last time, I'll go ahead and say the group 8 plus x squared to the 1/2 power minus 5x. We're trying to find its maximum and minimum values on the closed interval 3 to 5. So then I can say, oh, all right, let's take the derivative. 1/2 comes down in front of the group. Then times the group to the negative 1/2 power multiplied by the derivative of the inside, yet again, 2x, minus the derivative of 5x, which is 5. So now, just like the last problem, I can simplify this out. This time I'll get x over the square root of 8 plus x squared minus 5 equals 0. And again, just like the last problem, I'll move the 5 to the right-hand side. And then I would multiply by the square root on each side. Once I do that, I've got to get rid of the square root. So I square both sides. I get x squared is going to equal 5 squared for 25 times the square root squared, which is just what's inside the 8 plus x squared. At this point, I know I'm going to have a 25x squared on the right-hand side. If I subtract that on both sides, that's why the left-hand side becomes negative 24x squared. It was 1x squared minus 25x squared for negative 24x squared. 25 times 8 gave me 200 on the right. But now I would get x squared is equal to 200 divided by negative 24. Well, that reduces down to negative 25 over 3. But you can say, well, you didn't even need to bother to reduce it, John, because the fact that x squared is equaling a negative number means that it could only be an imaginary solution. So I can say, well, imaginary solutions means it doesn't have any true, real critical points. That's what I put right here. No real critical point, because an x squared term cannot equal a negative. So the only maxima or minima on this curve are at the beginning point and the end point. So I check those endpoints. When I plug in a 3 into the original expression, I had a negative 10.877, rounded to 3 decimal places. And when I plugged in the 5, I had a negative 19.255. Please now notice, I just entered those two values in, so you're just evaluating the endpoints in this problem since there's no critical points. And we have our maximum at the negative 10.877 and the minimum down further at negative 19.255. For 21, finally, oh, gorgeous, they get to trig functions. So now we're doing the exact same thing. We're trying to use the closed interval test and the extreme value theorem for a trigonometric function. So we can say, well, we know that the maximum or minimum values are going to occur at the endpoints listed here or at any critical point of this curve between those endpoints. So it's just a matter of, can we find the critical points? Of course we can. So when I looked at 21 here, I said, well, I'm going to take this gorgeous trigonometric function and take its derivative. I need to remember to take the derivative with the product rule. So that 10 sine x cosine x, I had to say, well, I need to first take the derivative of the first part. Derivative of 10 sine is 10 cosine x, of course, times the second cosine x. Then I have plus 10 sine x times the derivative of cosine x, which is negative sine x. And then trivially, you could say, ooh, plus the derivative of 8 is plus 0. So now it's just these two terms. And I thought, well, I'm going to go ahead and factor a 10 out of both of those terms. And then when I do that, I'll have cosine squared x and a negative sine squared x. So I have 10 times the group. Cosine squared minus sine squared is equal to 0. Now, this is in factored format, but I really can't do much with it right now. I know 10 can't equal 0. I could go ahead and ignore that, but this factor needs to be set equal to 0. It's more, or it would be easier to do that if I could get that in terms of one trigonometric function. That's what I did in the next step. I said, let's go ahead and just keep this in terms of cosine. I know thanks to the Pythagorean theorem of trigonometry, sine squared plus cosine squared is equal to 1. So sine squared is equal to 1 minus cosine squared. So in the place of sine squared, I just replaced it with 1 minus cosine squared. Now, inside of this group, that's going to give me cosine squared minus a negative cosine squared. That gives me 2 cosine squared x, and then of course I'll have my minus 1. You might have also remembered that all of these are your double angle formulas for the cosine function, where this and this is the other one. The other one is 1 minus 2 sine squared x. So I just put it in terms of cosine squared x minus 1. Now, that made it be able to be factored out. And I can say, using the zero product property, my solutions are either when the first factor equals 0, which can't happen, or the second factor equals 0. If the second factor equals 0, then we know 2 cosine squared x is equal to 1. Thus, cosine squared x is equal to 1 over 2. And then you can say, well, I need to take the square root of both sides. Yep. And when you do that, you need to remember the side not containing the variable you're solving for has to be the positive or negative square root. Well, the positive negative square root of 1 over 2, that's the same thing as the square root of 1 over the root of 2. If you rationalize and multiply by the root of 2 over the root of 2, you'll get plus or minus root of 2 over 2, which is more familiar with us on the unit circle. We know that the cosine is either positive or negative square root of 2 over 2 at any of the mid-quadrantal angles, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, all of those values. But the only value that's relevant for this problem is the midpoint of quadrant 1. So you can say, well, at pi over 4, the cosine is the square root of 2 over 2. Yeah, that's the critical point relevant for this region. And notice I put other solutions outside region. That's why there was no need to even mention them. Now, over here, my values of x that I test are the endpoints, and the only critical point within them, the pi over 4, I plugged that into my original function. And actually, this one I just did in my head because it's super easy. You know, when you plug in the 0, the sign of 0 is 0. So all of that is 0, you get plus 8. When you plug in pi over 2, well, the cosine of pi over 2 is 0. So all of that would be 0. You still get 8. The only value where you're going to get an answer is when you plug in the pi over 4. When you plug in the pi over 4, you'd have sine of pi over 4, cosine of pi over 4. Well, they're both the square root of 2 over 2. The square root of 2 over 2 times the square root of 2 over 2 would be 2 over 4, same thing as 1/2. You'd have 10 times 1/2 is 5. 5 plus 8 is 13. 13 is the y value at pi over 4. And you know clearly that's your maximum. And then either one of these can be listed as the minimum since they're the exact same value. So we have a minimum of 8, a maximum of 13. And you can see that that's precisely what I entered in on Achieve. For number 22, again, it gives me a trigonometric problem. This one's easier than the last one because the last one I had to use the product rule within the trigonometric formula. This time it's just y is equal to 16 theta minus 32 sine theta on the interval 0 to 2 pi. Okay, so when I looked at that, I said, all right, here's my function and its interval is 0 to 2 pi. I'll take its derivative. The derivative of 16 theta with respect to theta is simply 16. The derivative of 32 sine theta is going to be 32 cosine theta. So minus 32 sine theta becomes minus 32 cosine theta. I need to set this equal to 0 to find the critical points. And we can do that pretty easily by just saying 16 is going to equal positive 32 cosine of theta. So 16 over 32, or 1/2, is equal to the cosine of theta. At that point, you should be thinking in terms of the unit circle. The cosine of theta is 1/2 when the x component is 1/2 of a unit. We know x is 0 here, x is 1 here, so about halfway over. Now, trace that up and down to your curve. So you say, oh, well, the cosine is 1/2 at pi over 3 in quadrant 1, but it's also 1/2 at 5 pi over 3 in quadrant 4. Both of those have that horizontal component of 1/2. So both of those are going to be critical points in this problem, 0 to 2 pi. Notice I had to put the pi over 3 and 5 pi over 3 in there since both are critical points within this region. Now it just goes back to evaluating your original function at the endpoints and the two critical points within. When I did that, I had a y value of 0 at 0. You can see it pi over 3. It's really easy. You can pretty much do it in your head. You can say, well, that's going to be 16 times pi over 3. That's where the first part came from. The second part, we know that the sine function at pi over 3 is the square root of 3 over 2. So you're saying, well, it's going to be minus 32 times the square root of 3 over 2. That's minus 16 on the root of 3. Then at 5 pi over 3, same thing. 16 times 5 pi over 3 is 80 pi over 3. And then I'd have minus 32 times a negative square root of 3 over 2. That's where the plus 16 on the root of 3 came from. And I stress those exact values because this is one of the first type of problems in this section that I can recall that achieve once the exact values for your maximum and minimum. And I tested this one against the 32 pi. This was way greater than the 32 pi, which came surprising. I thought those would be close. But the maximum was at 80 pi over 3 plus 16 on the root of 3, and the minimum was at 16 pi over 3 minus 16 on the root of 3. And you can see that that's precisely how I entered it in on Achieve. And anytime it doesn't say anything about how much you need to round, you need to understand it's wanting an exact answer in problems like that. For 23, again, it's wanting an exact answer. And again, it gives us a good trigonometric function. We have y is equal to negative 5 tangent x plus 10x on the interval 0 to 1. So the work I did for this problem, next page. So the work I did on this problem here, I would say, well, if I have negative 5 tangent of x plus 10x on this interval, I need to first find my critical points and see if there are any between 0 and 1. Well, derivative of tangent is secant squared, so I get negative 5 secant squared x. And of course, the derivative of 10x is 10. I set this equal to 0 to find my critical point. When I do that, I can say, well, if I move the 5 secant x to the other side, it's going to be a positive 5 secant squared x. So I'd have 5 secant squared x is equal to 10. Divide by 5 on each side, secant squared x is 2. Myself, I would rather think of this in terms of cosine. So as soon as I get secant all by itself, I take the reciprocal of both sides. Reciprocal of secant squared is cosine squared. Reciprocal of 2 is 1/2. Now we saw this earlier. We could say, well, if you're trying to solve for x, then first you need to take the square root of both sides. And you'd say, well, the cosine of x is equal to the positive or negative square root of 1 over 2, which means the cosine of x is equal to the positive or negative square root of 2 over 2. So now I'm thinking, when is the cosine function positive or negative square root of 2 over 2? And I can say, well, that again, that's going to be at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. But the only one of those mid-quadrantal angles that are between 0 and 1 is your pi over 4. So the rest of them are irrelevant. And I can say this is the only critical point of relevance because it's within the region. So then it's just a matter of evaluating your function, and that's pretty easily done. We know that the tangent of 0 is 0, 10 times 0 is 0. So when you evaluate it 0, you get a 0. When you evaluate it pi over 4, we know that the tangent of pi over 4 is 1, since the sine and cosine are both the square root of 2 over 2 there. So you can say, well, that's just going to be negative 5 times 1 plus 10 times pi over 4, which gives me 5 pi over 2. That ended up being my maximum value. I did compare it against, and I had to use the calculator for this last one just to make sure that it wasn't as high as this number, and it's not. But I had to go to my calculator to do negative 5 tangent of 1 plus 10. This ended up being the highest value. Of course, the 0 is the lowest, but I didn't put the decimal approximation there simply because Achieve wanted the exact answers rather than any decimal approximation. For 24, this is the last of these extreme value theorem problems. We have a natural log of x divided by x on the interval 1 to 6, and we're trying to find its maximum and minimum value. So we say, all right, I go ahead, I take the derivative using the quotient rule, bring the denominator up to the numerator times the derivative of the numerator. Derivative of the natural log of x is 1 over x. Then we can say minus the numerator, which is the natural log of x, times the derivative of the denominator, that's just times 1, all over the denominator squared. Now, that gives me 1 minus the natural log of x over x squared. So I can say, well, all right, that's problematic because, well, actually, it's not problematic. It's easy because I know a fraction can only equal 0 when its numerator is equal to 0. That's what I said equal to 0. 1 minus the natural log of x is equal to 0. Now, the reason I said problematic is a lot of times I see students struggle solving logarithmic equations. You shouldn't struggle though. It's easy. We say, all right, once you get the logarithm by itself, what do? You get rid of it, the logarithm. How do you do that? You take the inverse of both sides of whatever that log. Natural log is log base e. The inverse of that is the exponential function base e. So we raise both sides of the equation into the exponent of an e, but that e and the natural log eliminate one another, and we're just left with x. So we got x is equal to e to the first. Now, is that value within the region in this problem? And I didn't write down my region here, but this problem wanted all x values between 1 and 6. Well, e is 2.718281828. So it's certainly in between there. So I'm evaluating at both endpoints and my one critical point within them. When I plug that into my function, when you plug in a 1, you know the natural log of 1 is 0. So you get a y value of 0 there. When you plug in your e, natural log of e is 1, and then you're dividing that by e, so we get 1 over e. And then at 6, you just get the natural log of 6 over 6. Now, I did have to go to my calculator because I wasn't sure that this was greater than that, but it is. Our 1 over e was slightly greater than the natural log of 6 over 6, so it's my maximum value. 0 is my minimum. And I went to achieve. And you can see I put 1 over e for my maximum, 0 for my minimum. They liked it. Now, I'm not crazy about how Achieve did these last two. It's trying to get you familiar with Rolle's theorem. Please remember, Rolle's theorem is just the idea that if a function on an interval, if it starts at the same value that it ends at, so if f of a is equal to f of b, then there is some x value called c in between a and b such that f prime of c is equal to 0. So all it's saying is what comes up must come down. So if your ending point is the same as your beginning point, then either every point in between has a derivative of 0 because it never increased or decreased, or if it did go up, in order for it to end up at the same point, at some point that we would call C, it had to turn and start going back down. Or if it went down to begin with, at some point, it had to go back up to get to that ending point at the same y value. And that point where it turned would be your critical point C. So it's asking us to show Rolle's theorem is verified in this function f of x is equal to x plus 5x to the negative 1. Now, unfortunately on Achieve, it doesn't have you do out the whole proof and all that stuff. It just has you find the value of C that shows Rolle's theorem works in this particular example. In my work, I've went ahead and did the full Rolle's theorem. Obviously, I can't see your work, so you don't have to do that to get credit for these problems. It would be wise if you did that, though, to get used to what I might want you to do on a test. So for this function, x plus 5x to the negative 1 on this interval, 1/4 to 20. First, I didn't want to take Achieve's word for it. I wanted to show that Rolle's theorem should apply. Rolle's theorem only applies if the y value at your endpoints are the same. Well, I plugged in a 1/4. I had 1/4 plus 5 times the reciprocal of 1/4 is 4. That gives me 20 plus 1/4, which is 81 over 4. I plugged in the other endpoint, 20, and I had 20 plus 5 times 20 to the negative 1, which means 5 over 20. That's 20 plus 1/4, or 81 over 4. Okay, so f of 1/4 is the same thing as f of 20. So Rolle's theorem would stipulate that there exists an x value equals c between these two x values of 1/4 and 20, where f prime of c is 0. That has to be the case. Either it's every single x value in between them has a slope of 0, and that's the reason the y values didn't change, or if the y values did change, and if they started off increasing, there's got to be some point C where they started decreasing to get back down to that original y value. So I can say, okay, we have to find f prime of c equal to 0. So I take the derivative. Derivative of f of x is just going to give you 1 minus 5x to the negative 2. I rewrote that as 1 minus 5 over x squared. We set that equal to 0 to find the critical point, or what we believe to be the critical point in this region. So when I do that, I can move the 5 over x squared to the right-hand side. Then from this step to this step, all I did is I multiplied both sides by x squared, which gives me x squared is equal to 5. Now, technically, the answer whenever you solve for x is you would say x should equal the positive or negative root of 5. I didn't bother with the negative because it would not be the critical point within the region that we need. But ooh, x equals the positive root of 5 fits in there perfectly. So then I can say, since x equals c equals the positive root of 5 belongs to the x values between 1/4 and 20, and clearly that derivative evaluated at the root of 5 would give you a derivative of 0. Rolle's theorem is verified. Now, again, I might ask you to do something like this on a test, the full verification proof. Achieve isn't capable of doing that. They're just wanting the wimpy little answer of the root of 5. And we put that in, we get credit for it. Now, the next one. And please remember, c is just the specific value of x where that derivative is 0, and c is the value in between 1 and 4. So whenever you're seeing that c equals, you're like, well, what? I thought it was x equals. C is a specific value of x that satisfies the criteria of Rolle's theorem. So now we have f of x is equal to a rational function, x squared over 5x minus 4. So I'll say, well, all right, let's try Rolle's theorem on this one. First thing I need to do to make sure Rolle's theorem applies, again, I don't just want to take the word of achieve that, yeah, it should apply for this problem. I want to evaluate my function at its beginning point, and I want to evaluate my function at its end point. Please notice when you do, f of 1 gives you 1 over 5 minus 4, which is just 1. F of 4, it would give you 16 over 20 minus 4, 16 over 16, again, 1. So f of 1 is equal to f of 4. Rolle's theorem states because of that, there has to be some x equals c between 1 and 4 where the derivative at that value of c is 0. It has to be. Okay, so now I will see about finding that. So I take my derivative here of my function and I use the quotient rule. I bring the denominator up to the numerator times the derivative of the numerator. Derivative of x squared is 2x. Minus the numerator times the derivative of the denominator, which is just 5, all over the denominator squared. Now I simplified this by just saying, well, I know if I multiply this first one out, I would get 10x to the second, but then I'm going to have minus 5x to the second. So that's just going to be 5x to the second. And then I'll also have a minus 8x. All over that denominator squared. Well, this derivative is going to equal 0 only when the numerator equals 0. So I set the numerator equal to 0. I can factor that numerator, and it would factor to be x times 5x minus 8. Now, using the zero product property, this tells us we have critical points at x equals 0 and at 5x equals 8 or x equals 8/5. So now the only critical point that's within our region and verifies Rolle's theorem is the second one. Yeah, there is also a critical point at 0, but that's irrelevant to our problem. Our problem and what Rolle's theorem stipulated is that there had to be a critical point in between 1 and 4. Well, there was. So I can say since x equals c, which is equal to 8/5, belongs to the set of x values between 1 and 4, and the derivative evaluated at 8/5 is 0, Rolle's theorem is verified. I feel like putting a quoterat demonstratum at the end of that because that's a pretty good proof problem. But of course, achieve just has you put in the value of c that satisfies Rolle's theorem for the 8/5, and you're done with that one. All right, guys, this will do it for section 4.2. You'll see our next two sections will be relatively similar. We're going to be doing the first derivative test in section 4.3 and the second derivative test in section 4.4 and talk about their implications on increasing and decreasing functions, and in 4.4 about upward and downward concavity of functions. Until then, but also, as always, please remember, if you have any questions, let me know. I'll be glad to help.